conference.
Okay, thank you for inviting me. It's great to be here. Can you hear me? Yeah. Okay, so I will talk about variational neural networks, the variational autoencoders, and various works related to that. And I like to start in a very simple way, sort of imagine you don't know much about machine learning and you start asking basic questions. And it will get more complicated over time. Okay, so the basic problem is this, right? We see some input and we'd like to know what is happening and what we should do. And when I say we, I kind of mean a system that we are trying to build. So the system should try to decide what to do. And so one idea is that let us understand what is happening, let the system understand what is happening. And maybe that will allow us to make good decisions. So now, what does it mean to understand? We don't completely know the question, but at least in my talk I will try to get a feeling of what that should look like. Okay, so one of the basic things we certainly want to do is to predict the future in one way or another. And so let's take a simple example. Imagine you have a car that is driving on the road and is approaching an intersection. And you would like to predict what you will see in a few seconds. So the car might go left or right. So it is incorrect to predict one specific image and say, you know, what you will see is somewhere close to that image, because these are two very different images. A better way to predict is to give a probability that it will go left or right, and then for each of the two situations you have a way of producing an image. Just make sure I have the okay, so what I just said, this is the picture of what I just said. So here you can imagine just a binary variable and you predict it, and then given the left you produce one image and given right you produce another image. So now if you want to imagine what will happen, and we have a model like this, then we'll simply decide, is it going left or is it going right? So we make a decision, okay, whether the car is going to go left or right and produce an image. So I will call these variables decisions. You can also call them latent variables. Okay. So if you do it a few times, each time we get some different picture, right? Okay, so now imagine now we observe what happens. And this observation resolves our uncertainty, right? So first we were unsure whether it was going left or right, and then observation resolves this uncertainty. And what also happens is that when we look at the image, we acquire some information about that image. And that information is coded in there, and hence is the Shannon's statement, information is the resolution of uncertainty. Okay. So now, there are many other things we won't know about, right, in here. Maybe there is some pedestrian, and is he going to cross the road or not? Will he smile? Where will his hands be? And is his head going to be sideways or straight? Or you can look at specific edge at a specific location and say, you know, which way is going to be oriented or so on, right? So there is a large number of things we won't know what they are, right? And we won't be able to predict. Now, if you want to imagine sharp image, we will have to make decisions about this. So to make a sharp image, we have to produce a very large number of decisions. Okay. Now, if you observe the image, then many of these uncertainties will be resolved. You will see where the pedestrian crossed the road or not, and so on. And so, is there a hope? So we can't possibly worry about all these details, right, if you model the world. Or can we worry about it? Okay. So can we capture all the decisions that are needed to produce data? So what is the amount of information about it, right? So you make a prediction about what you are going to see, and the things that you don't predict are the things that are going, no, there are a lot of things that are going to be resolved as you observe, and that's the information that you acquire about the image. And so the number of bits is the number of bits that you need to code that image, right? So if you predict something, and you need to, so imagine you have some model of the world, and you want to, imagine now yourself, you want to transmit that image to someone else, right? And imagine the other person has the same model as you. So if he makes the same predictions, then in order to imagine specific image, you have to tell him all the resolved decisions, all the information that you need to make that image, going from that prediction to make that image, right? So that number is huge, but it's not, in terms of conceptually, it's huge, right? In terms of number of decisions, but it's not that huge. It's just the number of bits it takes to code that, to code the data, and it does fit into a computer or a brain, so let's try that, okay? So it's instructable, okay? Now, the main point is that we don't know what these decisions are. We don't want to put some priors. We don't know how the world looks like. Well, some priors, but very generic ones. So we need to discover these decisions. So how do we discover them? So basic idea is that we build some model with large number of these decisions, and we tune these parameters. And so at the beginning, those decisions, those parameters have no meaning, and over time, these decisions acquire meaning. Okay, so what is the objective? So the objective is, we want to make a correct predictions, right? They should predict that something happens as often as it does in reality. And the things that are not predicted, things that are not predicted is the information needed to resolve these decisions. Okay, and equals the information needed to transmit the data. And so the criterion is the following, right? Make the best predictions, which is the same as information needed to resolve the data or the uncertainty, which is the same as maximizing the compression of the data, which is the same as maximizing likelihood of the data. These are all the same things, okay, in here. Okay, so how do we handle the huge number of decisions that need to generate input? And so we use the universal solution to all problems, right? We use deep, big, recurrent neural network with many latent variables in this case. And this is the hope. The hope is that learning such big, deep neural networks will discover conceptually meaningful decisions at high levels of hierarchy. Decisions such as will car go left or right, will the pedestrian cross the road, or even more basically, there are things such as cars and pedestrians. So basically, this is, I would say, the main goal of unsupervised deep learning. We would like to create representations like this. Okay, so now how do we code this? So we said we want to build this big network. So what we can imagine doing is splitting these decisions, like going left or right, some decision variables, and the deterministic computations that you do. So you can imagine this large number of decisions are going to feed into some deterministic neural network and produce input, and the different choices that you make in here will produce different inputs. Right? So this you can imagine some very complicated network. For example, it could be just deep network that looks something like this. Okay. So now how do we train these models? So we would like to know, as we observe the input, we would like to know how these decisions should be resolved, right? Now that's generally quite difficult. And so now imagine you create any function that would resolve these decisions. But you force this whole function to be such that you reconstruct the input exactly, okay? So what that means that if you do that, it means that you have coded, right, in all these decisions, the actual input, right? So you are compressing the input. You are coding the entire input, right? So if you now ask yourself, if you now decide, okay, I want to maximize the compression, right? Then you're going to learn something useful. You're going to capture these decisions. So basically what you do is you measure the amount of information that is put into resolving these decisions. Okay, so you go from some set of decisions to resolve decisions, that's some information, and you measure how much that information is, and you train the network to minimize this cost. This will be the total compression cost of your data. And this whole thing looks like an autoencoder. And so now what we are going to try to do is to implement it in such a way that you can train it by backpropagation. Okay. So the set of decisions you can imagine as a bunch of binary variables, but more generally, just imagine any variables, for example, real variables and so on. And more generally, you imagine some probability distribution, some prior distribution over these latent variables. Okay. And then when you resolve these decisions using this function, then you collapse, uncertainty about z into something more certain. So, for example, imagine you are uncertain at which location your car is, and then you look there, and maybe it's occluded, so you know roughly where it is. So now you know x more sharply, right? So you acquired some information about the input, and the information about the input is the number of bits that you need to go from here to here. And the number of bits that you need to go from here to here is actually just the KL divergence between these two distributions. Okay? So this is the cost that you have in the latent space. Now, usually it's much more convenient to put some of these decisions into here, right? So you imagine there's some decision, you go down and you get an input that you reconstruct, but it's hard to reconstruct exactly the x, right? So you reconstruct something, and then you still need some information to go from that reconstruction to the actual x. So we usually write it in this way as a probability of x given z. Okay, and the amount of bits that you need to code there is this. It's the log likelihood of this one. Okay. So basically, our goal is, so this is the total amount of bits that you need to code your input, okay? Now, that makes sense from an information point of view, but I usually find it much more believable if I actually see some mechanism for coding things, right? So you kind of believe the information theory, but maybe, right? But if you actually see that it can be coded, then you really believe it. Now, I really don't have time to explain the full coding idea, just give you some idea. Okay, so how do we actually code it? How do we code this information? How could we code it? So imagine you have some sequence of binary variables, and you look at the one binary variable, and we make a prediction about it. Let's say it's going to be 1 with probability 0.9. Then you can actually code this variable into this cost, using arithmetic coding, for example. And this, if you look at this cost, if you just plug in the numbers, you will find out that if you make roughly correct predictions, so let's say the value was 1, and you predict probability 0.9 that it's 1, then you will need only a few bits, but if it was 0, you kind of made the wrong prediction, you have to pay a lot of bits, okay? But you can use arithmetic coding to compress a bit into something like this. Okay, so how would we code discrete variable? How would we code a continuous variable now? So one way is to discretize, right? So we don't have probability distribution, but probability density. So if you want to turn it into probabilities, we discretize. And then the coding cost will be just this. And the more you discretize, the more bits you would need on, the more finely you discretize, the more bits you would need on average. Now, imagine, but the problem with this is that imagine you want to just code very few bits, like say 1 bit into this real variable. Then that would be hard, and it also would be very hard to backpropagate from such a thing. So, so what should we do? So one thing you can do is use this trick called bits backcoding by Geoff Hinton. And what you do is, rather than choosing this z, so this is our network, and it's going to output the variable z. Rather than choosing this z deterministically, right, there is always this decision, I know exactly what's happening, you just produce probability distribution. But rather than sampling from this distribution, you imagine you have some other stream of bits that are independent, and they are going to decide which value of z do you have. Okay? And then when you transmit it and the person recovers it, it recovers not only the bits that you wanted to transmit, but also the other bits. So the number of bits it costs you is actually this. Okay, so this is argument which you might want to think about separately. But when the dust settles, the point is that what you can do is you are able to code this variable z into this many bits. Okay. So it's basically the number of bits you need to go from pz to q of z given x. Okay, but the nice thing is imagine that compression scheme in there. Okay. Okay, so now how do we backpropagate through this? Okay, so we have this network, looks like an autoencoder, it has two specific cost functions, and we would like to backpropagate. So how are the sampling from functions implemented inside of a computer? You usually generate from some fixed distribution and pass it through a function, right? So if you want to generate from some Gaussian distribution, you can imagine generate from uniform and pass it through a linear function. Or you generate from unit Gaussian and then squash it around, right? So you can usually implement sampling in this fashion, right? You have a deterministic function all the way through that just gets noise injected into it, okay? But now the backpropagation is trivial because now you just backpropagate and the gradients that flow into here, they do nothing, right? Because there are no parameters in here. Okay. And this is the variational autoencoder. Okay. So this is the variational autoencoder that people talk about. So to summarize it, it's basically a normal autoencoder that has a specific cost functions that measure the number of bits that you need to code the data and that add noise to here, or that they sample from some distribution. Okay, so it's a noisy autoencoder with specific cost functions. Now, you can also ask, this is our generative model in here. Well, it's not good. Are you kidding? So this is our generative autoencoder in here. And you might ask, well, what would be the optimal queue? And the optimal queue is actually, if you could reverse this generative model, then the optimal queue would be this posterior in here. And, this is called, you find out that this cost that I have been describing is a variational bound on the true on the true likelihood. Okay, so I don't want to go through this math or anything, but I just want to point out. Okay. So now the generation from this model is very simple. So you have this prior distribution, you sample from it, you pass from neural network, and then you sample from X. So it's very simple. Okay, so I'm going to call this an information carrying layer. So this is some deterministic layer, and this is information carrying layer because it carries some information. It has some number of bits. So now, what do these layers look like? So variational autoencoders were introduced in these 3 papers. So this is for binary variables, and these are for Gaussian variables. So let me write it. Okay, so I'm going to write this layer in detail. What is it? So I'm going to just redraw this layer in this way, so I can write functions in it. So for Gaussian variables, this is how it looks like. You have the encoder network, which comes in here and produces these variables, these mu x and sigma x. And then you have the noise, which is always just sampled from unit Gaussian. And then you have this deterministic function, which just does this very simple operation. Okay? And then you output the z and the cost between this. So when you backpropagate, you just backpropagate this way. It's quite simple. Now, you can also you don't have to use, so here it was unit prior, right? Normally we have this unit prior. So this is our set of decisions. Now you can also put some other parameters, which can depend on other things like labels or something else in there. So you can have variables coming into here. Okay, so this is for Gaussian variables. And for binary variables, the situation is similar. You have the network that produces a bias. You pass the bias through sigmoid, and that gives you probability whether these various bits in here are 1s or 0. Okay. So now in that paper, we use also more non-trivial prior in here. So here is the motivation behind this. So when you go up and you produce a bias and you produce a sample, you get some binary sequence, right? And this whole thing is about compression, right? Find the best compression of the data. So when you have a sequence and you ask it to compress, right, you don't think of it as compressing bits independently, right? You say you go through sequence in an order and you predict the given bit from previous ones. Right? So in this paper, we use this very simple predictor. So we go through these bits in sequence, and we predict the given bit as a linear combination of previous ones, followed by sigmoid. And the nice thing about this functional form that is, while this is a sequential process, during training, this can be efficiently implemented, just using matrix operations. But the interesting thing is that if you want to sample from this model, you go sequentially. You sample the first one, and then given the sample of the first one affects the probability of the second one, okay? And then whatever was sampled in here affects the probability of the third one, and so on. So you have basically, the layers are often size, let's say 400, just as an example. So if you create a layer of size 400, then you have a generative model which is sort of like a 400 layers deep. It makes 400 sequential decisions. Okay, so within a single layer, you can get a depth of 400. Of course, there's some limited function, but still. And it's actually quite powerful. It gives very good results. Okay, so this is how these layers look like. So hopefully you have an idea how the variational autoencoder looks like now. Okay, so now I said that you would like to discover this huge number of decisions needed to produce the data, right? From edges to, is the car going to turn left or right? And the answer was that we should use a big neural network with many latent variables. So how do we construct such networks? So here is the basic variational autoencoder, and it has this information carrying layer. And I'm going to just simplify the notation a little bit. So this is the information layer, and these are the deterministic layers. Okay, so this is how it looks like. I'm just changing the color. And the point is that, you can come up with almost any autoencoder architecture. If you have an idea that how your architecture, deep neural network autoencoder should look like, you can turn it into a generative model, okay, by putting a bunch of these information carrying layers inside. Okay, so you can make almost any connections in here, right? But there are some rules. You, for example, cannot have a direct path from input to here. And the way you can imagine is, imagine yourself what would the generative model be. The generative model is just this part in here. So if I had connection that goes this way, I have no way of generating the data, right? Because I don't know this value in here. Okay. So these architectures are very flexible. Okay, so now let me discuss some basic architectures. So this is the most basic variational autoencoder. You have some input, you have some neural network in here, this goes into this information layer, and you go down in here. And the generative model is just this part. And then when you train it, then after it's trained, you can generate from it, and this is the generative model. And so you put a bunch of random numbers in here, and you get the different samples. So when you think about it, it's kind of remarkable, right? You just feed in a bunch of random numbers, and different random numbers will produce different pictures of digits. So Yann was talking about exactly this, the same sort of generative models as this one in the previous talk. We also try like this binarized Atari frames, so we had some locally connected networks, and these are 5 different games, and these are generated data, and these are like nearest neighbor examples. So you see that it does a reasonable job. This is, I think, freeway game, and this is Pong and Space Invaders. And so it's able to like generate like different scores and different lives and different configurations of these. But with some stuff it has problems, like really capturing all the objects at all locations. But I think it's a matter of training and stuff. So some more examples are in here. And okay, on NORB and image patches and faces. And then, oops, why is this not playing? Okay, so if you have a continuous space in here, then you can just move in it. And I think Ian was also talking about the same thing. So you can move in this space, and each of the points generate a different face. So you get this sort of image. So you see this face is slowly moving through space. And then what you can also do is you can condition on labels, and you say generate a digit 5 for me, okay? And then it will generate digit 5 for you. And then what they did in this paper is they trained this basic model, so I'm just drawing the generative model, and then they trained another model on the top, which had labels and a complementary information, and the complementary information is sort of the style. So now what you can ask is, okay, now let's fix the style and change the labels, and as you do that, you will get the different pictures. You get the same style of the digit, but a different label. And another question is, what is all these generative models good for? And we hope that it's going to learn a good representation, but we haven't had many examples of this really helping in tasks. And so this is one example where it helps, where it's in a semi-supervised learning, where let's say you take an M-list, and the generative model is able to train on everything, but for the classifications, you see only a few labels. So in this case, they got very good performance by just seeing these very few labels. Okay, so this was a basic static architecture. Now, we can make similar architecture for video. So there are many ways you can imagine modeling video, but one basic way is to sort of follow this autoencoder architecture. You take an input, you go through some encoder network into latent, and through decoder network into the reconstruction, right? And but because it's a video, what you can do is you can use recurrent network in here and recurrent network in here. And then this part is the generative model. So the way you generate data is just you feed the random numbers in here, and this produces different frames as it goes along. So this is rotating MNIST example. Okay, and this is a more complicated example, which is rotating bouncing MNIST with 2 digits. Okay, so this is quite complex actually when you think about it, because you have arbitrary 2 digits that are going at different speeds and at different rotations, and they are bouncing around. Okay, so we have been playing with these models for a while at DeepMind, and this one is with various people. We even generated a lot of these cool videos that you will see in here. Okay, and then these are some Atari games. Just the thing on the right is not generated here. Do we have arrow? Okay, so this is not generated on the right. We will get to generate it in a moment. So, but you can look at the game in here. And so this is on a binarized game of River Raid. And so you see that it generates these various objects moving and this spaceship flying here and shooting things. And then, I don't know why it doesn't give me the cursor. Oh, okay, so now this is the generated data on the right. So you see this road and this sort of cars passing by. So it's harder, but you see that it doesn't deteriorate over time. It's not like it suddenly disintegrates. It just keeps going. Okay. And then if you wait, it switches the road shape in here. And it's trying to do something with the score here too. And then, so this is now real video. Even though, not fully very complicated video, but nevertheless, it's a real video of people doing various motions. So in here, it's waving their hands, and here it's running. And so you see it's doing pretty decent job in there. It's not perfect. And it was also trained on transitions. So the network doesn't know that, the video has changed. So sometimes you see funny stuff happening, and then it converges onto another video. But again, the network doesn't disintegrate over time. Okay, so this is the information layer. So I will just make a few comments about how to build more architectures. So let me just cut it down and simplify it a little bit. Okay, so we have this thing going into approximate posterior queue, and this goes into prior. And let's just now not put any let's not draw the deterministic layers. Let's just put them into arrows. So the basic autoencoder is this architecture. You take an input. Now this will denote the neural network. The prior here was a unit Gaussian, and this goes down. So now you can make deeper generation and deeper inference if you want. So here are two stochastic layers, and the generative model is just this. So if you want to generate from this model, you would generate this one, then you generate this one, and then you generate input. And if you want to do inference, you take an input, you infer this one, and then you infer this one. Okay. So this is a valid model. If you want, you can switch this arrow, and it's still another model. And you can also decide to switch this arrow. Okay. But when you switch this arrow, you can ask yourself now, what is your generative model? And you see that this generation does not depend on this variable, right? The generative model is just this. So why would you want to create another stochastic variable if you don't actually use it for generation? So does that remind you of something? Okay, so this is basically, this is what you do in MCMC, right? You create a bunch of random variables, and eventually you end up with something, and you generate a picture from that, right? So this was done in this paper, which is a really nice paper. And yeah, it looks very simple. It's just like you are flipping the arrow, but it's a very good idea. And they actually do some, so you can make it deep. Okay, you can go like this. So the inference is deep. And they also use Hamiltonian Monte Carlo equation to learn the parameters. Okay. So, all right, so we have seen a few architectures, and we can ask, well, what is missing from them so far? Okay, so these are the architectures that I showed you. And you notice that they have a fixed depth, right? Because, okay, I can make it deep if I want. I can put in any number of layers I want, but it's fixed depth. Right? Even in temporal setting, right, if I want to go from here to here, it's a fixed depth. It goes like this, right? So if you sort of want to think of, more universal computations, like we humans, right? We think about stuff, and we can do very deep computation. And we do this deep computation in time, right? Because we think about it, right? And if you want to think of implementing universal computers, then we want to use the temporal depth, right? The depth of the recurrent networks. You know, the recurrent networks are basically universal computers. So you want to leverage depth of those, okay? So, so that at least there is deep inference in a few papers that in here, like the one I just mentioned. Although I don't know if the Monte Carlo really implements the universal computation, but at least it's a deeper model. It's a deeper inference. But the question is, how do we make it general, and how do we make generation also deep? Okay. And so, what can guide us is that, let's say, we want to analyze an image like this. So as humans, when we look at the image, we don't just go like, you take an input and we project to latent and do this, right? We look at one piece and then look at another piece and another piece, and we decide where we are going to look at the given time, right? And then when we look at one piece, we can sort of think about it for a while. We can say, what is this? It's a bicycle. And then we are going to move to another piece. So we can decide how much computation to do at the given moment when we do this, right? Similarly, we can look at this place, and then create a representation and say they are people, right? So we can look at various places and can create a representation and say these are the people. And then, if you reverse the process and you consider reconstruction, or better, if you consider generation or imagination, right? Similarly, if you want to imagine a scene like this, you don't usually just imagine everything in a single flash, right? You imagine, there is a building, and then there is a river, and then there are people, and then there are all these things, right? So the generative process should also be deep, and temporally deep. And then what you can also imagine doing is that you imagine some blurry version of something, or you draw a blurry version of something, and then you refine it, right? So you kind of roughly imagine there is a house, and then I'm going to refine it. And then if you imagine considering temporal data, then what you can imagine doing is decoupling computational time from real time. So if you treat video as just as a data, right, then you should be allowed to spend as much computation as you want on this video, right? You shouldn't need to necessarily follow the frames as you go through. And it sort of corresponds to looking at a YouTube video and rewinding it, right? But in the real world, you can sort of control what you see because you are actually in some control of what you are seeing, and maybe you can see things a few times. So you have sort of this ability. Okay, so here is our solution. We call it draw. And this was this current ICML paper. And so first I will show you what it does, and then I will walk you through that. So the draw reads frames, okay? Reads the input. It reconstructs input. So you see it's sequentially writing into various locations in the input. And you can imagine input. So these are pure imaginations. It learns how to draw digits. Okay, so this is the architecture. This is a recurrent network, and this is one time slice of the recurrent network. So there are several time slices. There is t-1, and there is t. Okay. And okay, so let me walk you through architecture, what it does. So there is an encoding network, and this encoding network decides at every time moment where to read. So it outputs sort of the location and scale of these variables, and it reads a little patch, and it goes into this network, and based on what the network just read, is going to decide the next moment where to move, and where to read again. Okay, so after read this patch, it's going to create a representation. But notice it doesn't have to take this data and produce the representation from this, right? It can take this data, it can think about it and do computation, and then output something and transmit some data put some information into this representation. Or it can read various pieces of data in here and then represent them in here, right? So it does these things that I was talking about. At least, theoretically, the architecture allows you to do this. And during reconstruction process, it's again, right? You want to say, I want to imagine a bicycle or something. So then you can do some computation and say, okay, how does the bicycle look like? And then you go and write it into an image. And when you write, it's just again sequentially writing. At every moment, it's writing a little piece into the data. And there is we also have this sort of arrow in here, so the network can also look what it has already written, and it can refine it, or it has seen what it has written, so now it knows where to go from there. And these are imaginations from the model. So when you generate, you just feed in a bunch of random numbers into this network, and the network makes decisions at every time point. And you see that it learned how to draw digits, which is very nice because this is how the digits came about. Somebody wrote them on a paper. So what are these read and write operations? So let's start with very simple read and write operations where they are just matrices. They're just fully connected matrices. So if you do that, then the generation is going to look like this. So rather than drawing it, it's going to draw, as if with a pen, it's going to draw a blur, and it's going to refine this blur as you go through. So at every point is make a decision. What sort of blurs should I make, and how should I change this blur, how should I refine it, and so on as you go through. And you can see how many decisions it's making at every time moment by looking at how many bits of information it's transferring at every time during training. So, and what you find is that this roughly similar number of decisions is transferred, similar number of bits is transferred at every point, and it sort of decays down at the end of the sequence. So basically, it is true that at every moment is making some decision, like what sort of blur am I going to do, and then how to refine it and so on. Okay. So now, what about the attention? So we can first ask, can this network already attend to part of the input? And the answer is yes, because it can just internally decide to ignore part of an input. But this is especially facilitated by the fact that it uses long short-term memory for the recurrent networks. And long-term memory has gates that gate the input and output, and so it can just decide to ignore part of the input. And this corresponds to covert attention in humans. So we can look at one place, like I'm looking there, but I can actually attend what's happening in here. Okay. So the LSTM network sort of sees an input, and then based on what it sees, it says, okay, now I should probably ignore this part of the image and pay attention to a different part. Okay. Now humans also have overt attention, which means moving eyes to a part of an image. So can we add that? And the answer is yes. We have already seen the video that it's there. So how do you do that? So in a simplest instance, you parameterize the attention window by 4 parameters. You say where, at which location you are reading, what is the scale, and what is the blur of the window. So you see here attention focused on here, and the thickness of the line is the blur, and this is the red patch. So it always outputs patch of a certain size, let's say 10 by 10. And so this is what it reads in this case. This is, you see, it reads a digit 5 sharply, and it draws a digit 5 in a blurry way in here. So when you take a image like that, it reads a patch like this. Now what you can also do, you can just reverse this operation. You can take a patch like that and say write it somewhere, and it's going to write it into an input. So how does it look inside of draw? So it's this. So you have encoding network. It outputs these 4 numbers in simplest case, and this is going to read the patch. And at every moment, it's going to output new set of numbers, and you read another patch, and so on. And for the writing, the decoder network now outputs both the patch to write and where it should write it. And it's going to write it into the output, but it's going to, so think of, well, this is going to be like a canvas, as Alex Grace calls it. So you imagine that, okay, at every point you write a little page, and over time you write a bunch of things in here until this gets filled up. And this canvas is this bias in a, in a sigmoid function of the binary probability distribution. So these are parameters that define the probability distribution over input given the latent. But anyway, it's basically writing into the output. And then, so now you can check how well it is doing on likelihoods of the data. So these are various methods, and this is the estimate, or in some cases, exact likelihood of on MLIST, and this is the variational bound. So the lower the better, and the bound is always larger than these numbers. So these are various methods like DBM and the NAID, and the Gaussian variational autoencoders in here. And then I don't have the new table. I forgot to put it. From this MCMC paper, where they actually use the convolutional version, and they get about 83 point something in here. These are the deep autoregressive networks, so this is the other variational autoencoder paper with binary variables. So this was the state of the art before. And so this is the draw without attention, and this is the draw with attention. So you see that it significantly outperforms the other methods. This is a big gap. Like if you look at the variations between these numbers, this is suddenly a big gap that you get in here. And so it's quite reassuring, right? When the network discovers how the digits were actually created, that they were drawn, right? Then that's where the thing performs so well. Okay. Okay. So now let me show you some more videos of what the draw does. So you have seen this. So the reading, writing, and generation. Then we try 2 MNIST digits. So these are 2 random MNIST digits placed on the background. And it's like a mini scene, right? You have 2 objects. And when you imagine a scene, you imagine maybe one object, then you imagine another object. So we wanted to see whether the network does that, and it does that. So if you look at, for example, here, it generates 1 digit, and then it generates another digit in there. So now this is a sort of more realistic example. So these are Google Street View house numbers. And these are not just nicely cropped house numbers when you just have one number. These are bigger numbers, a sequence of numbers. And these are all generated data except for this column. So this column is real data, close to this one. And these are all generated data, and this is the generation process. So you see that it's drawing it from the right to left, and it draws 1 digit, and then draws another digit, and so on. And you see that there is large variation. Sometimes there is 1 digit, 2 digit, 3 digits, 4 digits, and there could be different slopes and different colors and different styles of this. Okay, so yeah, so these are Street View house numbers generations. And these are CFAR-generated data. So now you have seen one already in the previous, some already in the previous talk. So it's hard to visually compare which one is better, right? One difference you will see is that these are not as sharp. So as Ian was saying, these models have harder time generating sharp images. But they have reasonable structure. You can sort of say maybe there are objects in here, but of course, like I don't know what it is. But of course, you cannot really expect to generate these, because if you did that, you would definitely be overfitting. There is only 60,000 examples in there. And these are faces. And so these are much harder faces than the ones I showed you before, because they are at a different, people are in different pose, okay, in here. So, yeah. Okay, so to summarize what the draw does, it has a flexible temporally deep inference. It has a flexible temporally deep generation. It has an attention, but it is also very general architecture. So we all did it we did it all on images, but it could be applied to any kind of data, and it can be combined with any attention mechanism. It doesn't have to be that specific two-dimensional attention mechanism that you have in there. And then this temporal data that I've said are actually special case of the draw. So if you have a video and you say at every time moment, rather than reading from the entire video, I read from the current frame and write into current frame and go sequentially, then you get the basic the temporal architecture that I showed you before. And yeah, so these are just the various, this is just to show you a lot of videos that I have showed you before. Okay, and so now finally let's discuss some, let's discuss, so we discuss compressing the data, right? All your data. But we never talk about compressing the model, right? We only compress the activations. So could we also measure the complexity of the model? Now, even if you don't do that, we can still do a good job, because we could split the training set and we can split the data into training and test set, and we can find the good parameters by cross-validation. But if you actually properly measure complexity of the model, you might remove the need for cross-validation. Okay, so how would we do that? So what is our model? So this was our model, and now I make the weights explicit, right? This is the generative model. We make decisions. These are the latent variables, and then this is the probability of input given latent variables. And probability of input is sum over the z, okay, in here. Now, if you want to specify complexity of the model, we have to explain various things. We have to explain that it is a neural network, how many layers it has, how it computes stuff, and what are the values of these weights. Now, it is hard to measure these various things, right? But one thing you can imagine doing is just to write a code. You look at the code of your length of your program on a computer and say, okay, that's the complexity of it, right? But it also depends on the platform that you are using. And, either way, if you try different networks and different sorts of models, they are going to have roughly the same length, everything except for the weights, right? So we are going to just worry about the weights W, okay? How do we compress the weights? So how do we compress the weights? How do we code the weights? So this was the model that we had before. This was the generative model. And we did a variational autoencoding, right? So we did this approximate inference where we produce probability distribution over z given the x and some other parameters in the encoder, and we minimize the variational bound, or the number of bits. So number of bits in latents and number of bits in the inputs. So this is what we did before. So now how do we measure complexity of the model? So we can just add that into this parameter. So the way we generate data, we'll pick some weights from some prior distribution. Like you can imagine uniform Gaussian on the weights, for example, right? So we pick weights from uniform Gaussian, and then we pick the activations, we make decisions about the latent variables, and then we generate the x. Okay, so we can imagine doing that. And now, what do these things correspond to? So I interpreted z before as, for example, the car goes and it might turn left or right. Okay, yeah, I'm done. Yeah, the car might go left or right, and so by observing that, you resolve the uncertainty about whether it goes left or right. Now, what is the meaning of this? So as you go through the world, so this is basically a set of models of the world that you have, right? How the world can look like. And at the beginning, you are completely unsure about what it is, but as you observe the world, it will resolve the uncertainty about what those models of the world are like. Okay, so you become much more confident now about what the model, what the world looks like as you observe the data. And here is, and so you can do the same trick, right? Rather than having just one, Q for Z, you can also have Q for W, and do the same thing, right? So now notice there is a slight difference. There is one set of weights for all your data, and there is a different Z for every data point. But other than that, you can use the same thing, and you can use the KL divergence between these to compress the data. And there are some simple experiments in this paper, and there are various other papers before doing similar stuff. I put the reference earlier there, that this stuff actually works. Okay, so in conclusion, we are able to train large models with latent variables, and the large models are necessary for modeling the real world, and it's a simple autoencoding framework with backpropagation training. So if you know how to train neural networks and autoencoders, it's simple to turn them into generative models. Now, it's a little harder to train because there is noise in there, and there are these cost functions, but it's overall quite, it's a very simple framework. It does probabilistic modeling, it does fast generation, we are able to focus on subset of a data, we can make flexible temporally deep inference, and decide how much computation to do on a given piece of data, and we can do flexible temporally deep generation, decide how much computation to do when we want to imagine data, and we are able to consider uncertainty or the coding cost of the model.